Very good evening, everyone. On behalf of the entire Edumitra team, it is with great enthusiasm that I extend a warm and heartfelt welcome to Sharat Prabhu sir, who will be guiding us through the exciting journey of this 5-day International Space Olympiad training. Sharat sir is not just a seasoned physicist, but an inspiring science communicator with a deep passion for promoting scientific thinking and education. With an impressive academic background, including a postgraduate degree in physics and an MPhil specialization in astrophysics, Sharat Sir's expertise in high energy astrophysics, particularly his research in gamma ray burst, speaks volumes about his dedication and curiosity in unveiling the mysteries of the universe. Beyond his academic achievements, Sharat Sir is a multifaceted individual whose contribution to science popularization are truly remarkable. Hosting the astronomy TV show Ariki Agasham on the Malayalam education channel Victors, he has captured the imagination of a vast audience, making complex scientific concepts accessible to and engaging. We are honored and thrilled to have you with us, Sharat Sir, to lead this training program. Your wealth and knowledge, engaging teaching style, and passion for science will make these 5 days not only educational but also incredibly inspiring for everyone present.
Thank you, Edumitra, and
Yeah,
I
over to you,
hope I am.
Sharat sir.
Yeah,
Yeah,
thank you.
welcome.
I hope I am audible well. Yes. Okay. So, I good evening to all. I think some of you, it's good morning. Maybe this here in India. I'm talking from India, so it is good evening here. Anyway, a warm welcome to all my dear students. And today, for coming 4 days, I will be here to give you some insights about the syllabus for your upcoming examination of ISO, and I will be giving you a brief overview of all the syllabus things. I cannot completely teach you every bit of things, but I will cover as much as possible. And I am planning this class in such a way that the first 1 hour completely dedicated to my lecture. Okay, my lecture means it's not just a talk. I will give you some presentation. Maybe I will draw something in the board, something like that. So during that entire 1 hour, you are not allowed to unmute, or you cannot ask me any questions, but in between that, if there is any doubt, you can put that in the chat. I will take those questions only at the end of the session. That means after 1 hour we will take the questions and I will answer it one by one. Okay, so since it is a crowded thing, because almost 50 participants are there, I am not sure that I can ask you one by one by unmuting. If we have time at the end, then we can have the an audible questions, or the instead of chat you can ask me directly as well, but wait for the end. So meanwhile, during the class, if you have any doubt, if you need any clarification about anything, you can put that in the chat. Maybe in between the class itself, I will try to take some questions from that if it is relevant, or otherwise I will try to answer or as much as possible at the end of the session after 1 hour. I hope it is clear, and let's begin. Let me share my screen. Okay. Yes. Okay, here, let's begin. So this is just an image that is generated by ChatGPT, where I have given something like the input for that image. The prompt for that image is something like the measurements in astronomy. So the measurements in astronomy, that is basically your first initial topic. Okay, so but entire measurements of astronomy is not covered there anyway. So what do you mean by measurements? So you all know how to measure something, not everything, but at least you might have measured the length of it. So if suppose I draw a straight line, supposed to be a straight line, a red line that you can see right now on the screen, and this, just a second. Okay, so this line, if you want to measure its length, it's so easy for you. Okay, if I ask you to measure the length of this line, you can take a scale, that's a ruler in your geometry box, and put it near to that, and you can easily measure the length of that. Something like a scale you can see here. You can place something near to that and measure the distance. So simple. Okay, so that is how. Okay, that is how we can measure the simple lengths in your notebook, maybe the size of your the length of your table, or even the length of yourself, or maybe something the size of your room, like that. Everything can be easily measured. And there is one more interesting another kind of measurement, that you know how to measure the mass. Okay, so if you want to weigh yourself, you have a weighing balance, you can stand on that and measure the weight. And uh, if you have some fever or something like that, we measure the body temperature by using a thermometer, simply putting it on your in your armpit, or maybe into your mouth or something like that. Then you can easily measure the body temperature. So these things that we do regularly, so the measurements are not a big deal, or a, what to say, it is not an unfamiliar things to you. Okay, and there are other things that we are not purposefully measuring, but when you drive on a car or something, you can see its speed, actually, that is written on the dashboard, that it will be there. What is the range that it can travel, and what is the speed at which it is traveling, how far you have traveled. All these things are being measured in a car, something like that. So measurements are there everywhere, and measurements are so important in the world of science, actually. So if you want to prove something, you should be able to measure it. Okay, so that is how the science works. But there is a major issue when it comes to astronomy. So in your physics lab, maybe in your school classes, everything can be easily measured in your physics lab or chemistry lab, maybe in biology lab, wherever. So in your lab, you can easily measure things. But in the case of astronomy, if you want to measure the temperature of sun, we cannot put a thermometer into the mouth or into the sun and measure its temperature. There is no such thermometer is there, and we cannot go there and put it there. Okay, so it is impossible for that. And suppose if you want to measure the circumference of Earth, how can you do that? There is no such long measuring tape just to circumnavigate the Earth. Okay, maybe we can imagine, at least we can circumnavigate the Earth by traveling. It's okay. But what about the distance to Moon? Or maybe moon we have already traveled, but what about the distance to sun, maybe to another galaxy or another star? Okay, such kind of things. So when you google for some result, what is the distance to the Andromeda galaxy, you get a number there, a huge number. And how astronomers measured that distance, that's a question. That's an interesting question. Actually, we cannot have a meter or a tape or something like a measure tape or anything to go there directly and measure it. Okay, so the only thing, it is not just about the distance, temperature, maybe the mass of a planet, mass of a star, and what is the composition of a star. A star or a planet consists of maybe hydrogen, helium, calcium. We say like this, okay? Or you might have read many places that a star, sun consists of mostly hydrogen. So how we know that there is hydrogen? How we measured that? Or have we done any experiment by bringing some material from sun into a chemistry lab and did some experiment to find whether it is consist of hydrogen or helium? So we don't know that. Okay. Or another way, we haven't done anything like that, but instead we have only observed the night sky. So one more thing, this is a picture of night sky, that's all. You can see a band here, and that is the Milky Way. And you can see a famous comet that recently came to the sky, that is, you can see here as a small streak, that's a comet actually. And this bright one is not actually the a sun or anything, it is actually the Venus. Okay, so this is just the night sky. And all the things what I mentioned in the last slide, like the temperature, the mass, the speed at which a star is moving or a galaxy is moving, or at what speed the sun is rotating, or what is the distance to nearby stars like Proxima Centauri. So all these things can only be measured by observing the night sky. Okay, the only way to gather information is only by receiving light. Okay, so just think that we have only one thing. Okay, so if you are observing a star, what we receive here is nothing else. That is basically the light. Okay, so light is basically or mostly the one and only thing that we get here on the surface of Earth. Or maybe we can imagine light in the space as well. So since there are space telescopes, the telescope that are revolving above our atmosphere around Earth, it is there. So those telescope can also only receive light from us. So all the things like the temperature, the distance, the mass, the composition, the velocity, all these kind of different things has to be measured or quantified only by analyzing the light that is coming from celestial objects. So that is one interesting thing about astronomy. We don't have any direct access to all these things. We have only light is coming here, and using those light we can measure things. Okay, so when you hear light or when we hear the word light, it's there is no need to simply explain that. In normally it is well understood that you can see things, and there might be a light source, and light is coming from your screen right now. That is why you can see what I'm teaching here, and all those things are there. Okay, so light is not an unfamiliar thing to anyone, but in astronomy we have to give much more attention, because in astronomy there are many kind of lights. Okay, or astronomers call many things as light. Okay, so this is just take the picture from the corner. Okay, so here you can see a graph kind of thing you can see. So this is about here, just leave all other things. I first let's go one by one. You can see here one is written as gamma rays, and here you can see another interesting thing that is actually starts from violet and ends at red. That is violet, indigo, blue, green, red, orange. Okay, green, uh, yes, then yellow, orange, red. So you can see that rainbow of colors. Okay, so what we mean by that rainbow of colors, so these are some kind of lights, or these are the only lights which is visible to human being. So people like us can only see this much light. Okay, this type of light, and that type of light is called a visible light. So using that visible light, if you are seeing something around you, that is simply because there is visible light is there, that is sensible for your eye. But there are lights which we cannot see. The best example is the top one, top left. You can see, you hopefully know what it is. This is called an X-ray. Okay, an X-ray image. That means when there is a fracture or something for your hand or something like that, something suspicious inside your body, usually the doctors take an X-ray. Okay, so when that X-ray is taking, if you have an experience like that, you cannot see any light or any flash. But instead of that, if you go to a studio to take a photo of yourself, then there will be some kind of light flashing on your body, so you can see when the picture has been taken, or you can understand. But in the case of an X-ray, you cannot see anything, but finally you get a result like this. Okay, there is no flash or anything you can see. But actually, even for an X-ray, there is a flash. But the problem is that our own eyes, our human eyes cannot see them. But once it is into a film or into a digital screen, those lights can be converted to visible light, so that we can see it like this. Okay, so this is a best example. And there is another thing that there are some kind of other waves called the microwaves are there. So microwaves are a kind of waves that is happening, that is there are many kind of microwaves, and a specific frequency, a specific type of microwave in your microwave oven. Okay, in that oven, actually that particular frequency is being produced there, but you cannot see that. Okay, of course, obviously there will be an ambient inside, there will be a light, but that is not microwave. Actually, for a microwave cooking, you cannot see that microwave. Okay, but with proper sensors and all, we are able to see microwave as well. So that is another thing. And here you can see another photograph of a city, maybe a town or something like that, you can see. And in that you can see all the things are actually color coded. Okay, so this is what a result from an infrared camera. Okay, so if you have a camera which is capable of seeing in infrared, if you take a picture of a city, it will looks like something like this. So the hot places will be in pink and red, and the cool places will be in yellow or green, something like that. So you can see that because of lot of friction, the rod is so hot. Okay, and this footpath, you can see there is not much friction because of any car or anything, so it is not that high in temperature. So this is what an infrared camera sees. Okay, but we cannot see it directly because our eye cannot see like this, but we need a tool like the infrared camera so that we can see. So this is another type of light. And another best example you can see, I don't know you are familiar with this thing, this is called a radio, and this actually uses something like another type of wave called uh, another type of waves called radio waves. The best example is that if you have a Wi-Fi in your home, so that Wi-Fi is communicating with your phone, that you are getting internet through that Wi-Fi, you cannot see anything coming from your Wi-Fi modem. So from your Wi-Fi router, you cannot see anything that is coming from that. Okay, but there are some invisible. Okay, there are some invisible. Just a second. Yeah, there are some invisible light is coming from that Wi-Fi modem. They actually called radio waves. So there are many, apart from this visible light, there are many kind of lights including gamma ray, X-ray, ultraviolet, infrared, microwave, radio waves. So there are many types of light that are actually coming to the surface of maybe to the surface of Earth or maybe to space. So there are this kind of lights, but for human eye we can only see this visible light. All the other, even though we cannot see with the bare eye, even we cannot see, we have those the humanity actually made sensors or some kind of tools to detect all of them. So even though we cannot see, the human eye cannot see, we have instruments that are capable of reading or seeing in all these lights. Okay, so that is why we have all this. So these are different types of lights. So in astronomy, generally we say that all of them are light. Okay, especially, but in usual terms, these gamma ray, X-ray, ultraviolets are not light. But in astronomy, astronomers call them as light because all these types of lights, gamma ray, X-ray, ultraviolet, infrared, visible light, microwave, radio waves, all of them are being used in astronomy to observe celestial bodies. Okay, so we are not just observing something in the sky, a galaxy or something, not just in the visible light. Usual telescope, like the general telescope that what we buy from Amazon or eBay, and that is what you are seeing or using for observation, that amateur telescopes, they can only see in what is called the visible light. So that is what we use for general public observation. But in the case of other telescopes, something like the professional telescope, they are actually able to see in other lights as well. Okay, so that is how. And one more interesting thing is that we are talking not about the X-ray or the microwave or that is happening on the surface of Earth or in household things or in medical field or anything, but we are actually discussing about the celestial things or astronomical things. So all the lights are coming from the skies or maybe from space that is light years away. So then there is another problem. All these lights cannot enter into the Earth's atmosphere. You can see that here visible light can actually come to the Earth's surface, and some infrared can also come to the Earth's atmosphere. And so I will explain once again. So imagine that there is a galaxy, okay, which is so far away, and the light is actually coming from, sorry, okay, so the light is actually coming from those that galaxy, okay, from that okay, from that galaxy. But light means there is gamma ray, X-ray, visible light, all kind of lights are actually coming from there. But in that case, only the atmosphere will only allow the passage of visible light to the Earth's atmosphere or the ground, and also some radio waves. Almost all other types of waves, like something like gamma rays, X-rays, ultraviolets, all are blocked by the atmosphere of our Earth. That is why if you want to have an observation in X-ray or gamma ray, maybe in infrared, we need to send the telescope to the space. Okay, that is why we have one reason, that is why we have space telescope, or the most important reason why we do have space telescope is that all kind of lights are not reaching on the surface of Earth. So you know that there is a recent famous telescope called the JWST, that is the James Webb Space Telescope, which is actually seeing not in the visible light, it is actually capable of seeing in infrared light. So that infrared telescope, we can call it as an infrared telescope because it is seeing in infrared. So that infrared telescope is able to see in infrared, and we cannot keep it on the Earth's surface. Okay, so it is better to send it to space so that it can get all the infrared which is coming from the outer space or far away distances. Okay, so that is why we send telescope to space. Okay, and I will give you some examples of different types of telescope. You can see this is an X-ray or gamma ray telescope on the top left. Then this is the famous JWST, which is capable of observing in infrared. And here in the right bottom corner, you can see that something like a dish antenna. That giant dish is actually a kind of a telescope, not a kind of a telescope, it is a telescope, but that is a radio telescope which is capable of seeing the space in radio. And you can see here, this is the most famous Hubble Space Telescope, which is able to see mostly in visible and some ultraviolet and some infrared it is capable of seeing. And here on the bottom left, you can see it is an optical telescope which is capable of seeing in visible light. So there are many kind of telescopes out there, so which are capable, each of them are capable of seeing in a particular kind of light so that it can get different information as well. And this is mostly happening. Okay, so most of the information that we know about astronomy is by analyzing light. So light means not just the visible light, that is the rainbow of colors, but apart from, there are many kind of lights are there which is invisible for the human eye. Okay, now let's go ahead. And not just the light, there are some other things also being measured by the astronomers. Okay, but not much when compared with the light. It is actually not much. Gravitational waves are also being observed by astronomers. Cosmic rays are also being observed by astronomers, and neutrinos are also being received and observed by astronomers. So these are not lights anyway. So the light means all these types of lights are okay, and that is the major part of astronomy. And a few or the remaining slides part is actually other than the light, which is gravitational waves, cosmic rays, and neutrinos. Okay, so these are all some kind of, so something like this small, this is actually a cosmic ray observatory, and this is a neutron observatory, and this is a gravitational wave observatory. Okay, let's go ahead and see how astronomers measure distance. Okay, so distance measurement is an interesting thing. So I will give you a simple idea about that. Okay, before going into that. Okay, so sometimes or maybe in our daily life cases, if you want to measure the distance to something, it is easy to use a long tape or something like a long scale or anything. But imagine that if you want to measure the height of a mountain or maybe height of a big tree. Okay, height of a tree. Okay. So assume that there is a tree here. Okay, I'm giving you an example where you cannot directly go and measure. Okay, so if I want to measure the height of this tree, it is so large, and imagine that there are some maybe some snakes are there, so that I cannot go and climb to measure the distance. So if I can climb, it is easy. I can drop a long thread with a stone hanging from the top, and when it reach the bottom, I can measure the length of the string. So it is easy to measure something like this. But imagine that you cannot access that tree, it is far away. Okay, and if you want to measure the height of that tree, there is an interesting method. Okay, instead of climbing up the tree, you can stand here. Okay, and take a pipe and look through that. You can observe the top of the, sorry, okay, you can observe the top of the tree through a pipe, a simple pipe. It is not a telescope or anything. Sometimes you can use a kind of a simple telescope or maybe, but a simple pipe so that you can see the top. Okay, now you can measure So now you can imagine a triangle here. So I am looking through here, and this look itself, or my eyesight through this line, this is one side, and height of the tree and the distance to the tree. So it will make something like a triangle. Okay, I'm not talking about the astronomical thing, but it has connection to astronomy. That's why I mentioned. So you got a triangle. This is the height of the tree, and this is the distance to tree. Okay, clear? So this is the distance to tree, this is the height of the tree, and I don't know what it is. This is a, maybe to complete the triangle I need this as well. So for a triangle there are three angles. That is why it is called triangle. Okay, so we can measure this angle as well. Okay, I'm not explaining how to measure that because you are all junior batch students. So but in your higher classes, or you will learn how to measure those angles and all. So once you get that angle, and if you know this distance, then you can find the height of the tree. Okay, so what you need to know? You need to know this angle and you need to know this distance. Okay, so that you can easily find the height of this tree. Okay, so this is how maybe people can measure the height of trees. And you know that if you want to measure the height of a mountain or something like that, a peak or something like that, the way the surveyors measure the height of that tree is using this kind of method, using the mathematics of triangles. Okay, and that field of mathematics is called trigonometry. Don't worry about these things, you will learn all these things in your higher classes. It is called a trigonometry. Sorry, not metry, it is metry. Okay, so this is the mathematics of triangles. So using the mathematics of triangles, we can actually measure the height of the tree or a height of a mountain without going to the top of the mountain or top of the tree. What you need to know, only this distance, which you can measure with a tape or something like that. Then you can measure this angle using some tools, and using all these things you can measure the height of a tree. Simple. Okay, it is not that simple, but anyway, you just imagine that something which is not accessible directly can be measured without even going to the top of that. Or maybe if you modify this to some more complex way, then you can even measure the height of this thing without even measuring this distance. So there are many ways for that you will learn it in the high classes, and you will do this kind of maths problems as well. So don't worry about it. Anyway, the idea is that you can measure things without even touching those things, or without even accessing it completely. Okay, so this is the similar case for astronomy as well. If you want to measure the distance to moon, you cannot go and touch the moon directly, but we have to find some way to measure the distance to those planets, maybe to star or galaxy, by sitting on the earth itself. So that are some remote methods. We can call it as a remote method. Remote in the sense that we cannot directly access it. Okay, we have to sit here and remotely measure the distance. So that we can say that this kind of a remote measurement without directly accessing them. So for that, there are many different methods, especially for distance measurement. There are many different methods are there. Depending on the distance at which you are measuring, the astronomers use different kind of methods. And that thing is called cosmic distance ladder. Okay, so this is some example. I will go into each of them separately, don't worry. So the easy thing, especially for the inner solar system, so the solar radar ranging is there. So the radar ranging, the idea is so simple, okay, but it is not much discussed in astronomy usually. But anyway, for the completion of the topic, I will discuss that. So radar ranging means, assume that there is an object here. Okay, so suppose Venus is here. Okay, Venus is the nearby planet for us, and Venus is here, and the Earth is here, and I want to measure the distance to Venus. Okay, so what I can do is that I can send a radio wave, okay, a light, a radio pulse, and that radio wave can travel through the space, okay, and it can go there and reflect back. Okay, it can come back. So it will go there and come back, reflect back. It is something like a ball. So when you throw a ball to something, it can get hit on that object and it can come back, reflect back, like that. But instead of ball or anything, we cannot send ball to Venus or anything. We can send light. That is, which kind of light? Radio light. and that radio light can go there and come back, and simply we can measure the time taken to go there and come back. Okay, so we start it from here. Okay, the light pulse is started from here, or the radio wave is started from here, then we start a stopwatch, and from the stopwatch we get the time taken for the radio waves to make a complete travel, a round trip from a trip from Earth to Venus and Venus to that. So from that time, okay, we can measure the distance. So that is called the radar ranging. So this is how actually you know that the radar is everywhere. Even for flight navigation and all, people use this radar ranging methods. Okay, using that we can, not only that, okay, radar ranging has another advantage. It can detect the distance. At the same time, it can also detect the velocity as well. Okay, so velocity means speed. Okay, so it can measure the speed, it can measure the distance, and so this is how actually the flight navigations are happening. Especially you can see something that is rotating like in an airport and all, so they are actually radars. So those radars are capable of detecting the flight that is coming and how far away it is, things like that. So that is the radar ranging. Okay, so radar ranging is not applicable for farther away from the solar system. Okay, it only works for solar system, especially the inner solar system, maybe up to Mars or something like that. Beyond that, it is not applicable. Okay, so that is why we have something called distance ladder. So for nearby objects like Moon, maybe Venus, Mercury, Mars and all, we can use this thing called radar ranging. So beyond that, there are stars we want to measure. So how will we measure the distance to nearby stars? So we have another method, but it has limitation. We cannot use it for everything. So especially for the farther away stars, we need to use some other things, that is called a main sequence fitting, and even farther away things to nearby galaxies and all. So within the for nearby stars we can use parallax method, and within the Milky Way, inside the Milky Way, we can use main sequence fitting. So I will explain what is parallax and Cepheids later. Main sequence I won't be today, but Cepheids and parallax I will discuss today. Don't worry about that. Okay, this main sequence fittings is actually not that easy for you, so that's why I won't be discussing that for you. But anyway, just understand that there is a method called the main sequence fitting that is used for Milky Way. So if you want to measure the distance within the Milky Way, then we can use main sequence fitting, but it is limited. We can only use it for the within the Milky Way. If you want to go farther to the nearby galaxies, something, if you want to measure the distance to another galaxy, then we cannot use the ranging or the this parallax method or the main sequence. Then we have to use something called Cepheids method or standard candle method or something like that. Just leave the name. Anyway, that is one method. And if you want to measure to distance to not just to nearby galaxies, if you want to measure the distance to galaxy clusters, okay, maybe something, you can see that here the distance is written. So galaxy clusters or so, then they use something called supernovae. Okay, so there are some kind of supernovae which is using which they can actually find the distance. So then another methods are there, and if beyond that, if you want to measure the distance even beyond that, then they use something called the Hubble's law. So this you will learn at the end of in the last day of the session, so don't worry about that. So these are called distance ladders. So why we do have a ladder? It is like climbing a ladder. That means you are actually going farther away from the Earth. So here for the nearby system or nearby solar system object, we use radar ranging. If you want to measure the distance to nearby stars, okay, you can see the distance as well. Just see here, it is written as Ly. So I will explain what is Ly is. Ly means light year. Okay. Hopefully you know that. Anyway, I am explaining it for the completeness. So light year means is a method, okay, or is a unit, not a method. It's a unit that is used to measure the distance. So why we need units? So if you want to measure the thickness of some small pipe or anything, we use something called a millimeter. And if you want to measure the length of your textbook, then we will use centimeter. In the same way, if you want to measure the distance to your school from your home, then we will use something called kilometer. Okay, so why we are using all of this? Instead of this everything, instead of kilometer you can use millimeter or centimeter. It's actually possible, but the problem is that when you are using small a millimeter for measuring a large distance, the number will be so large. Okay, so that is the problem. So instead of that, we can use larger units like kilometer or centimeter, maybe even beyond that. That is actually useful for measuring distance, and you can use the numbers conveniently. So for convenience, we use larger units, and one of the popular units that is used by astronomers is actually light year. So it is a unit of distance. Okay, so what is light year? So it is defined as it is the distance traveled by light in a year. So if we give light 1 year of time, it can travel a certain distance. That long distance is called a light year. So if we give 1 second for light, okay, if I am giving, suppose that 1 second is given for light, the light can travel 3,0,0,0,0. So this 3 lakh, okay, or 300,000 kilometers can be traveled in a second. So that fast the light is. Within a second, it can travel almost 3 lakh kilometer or 300,000 kilometers. So that is in 1 second. What is in 2 seconds? What if I am giving it 2 seconds? I have to multiply it with a 2. So what if it is 10 seconds? I have to multiply it with a 10. So similarly, in a minute, okay, so a minute consists of 60 seconds. So in a minute, the light can travel this much distance. So I have to multiply it with it. So when I multiply, I get 18. Then how many zeros? 6 zeros. So this is 18 million kilometer can be traveled by light in a minute. So in an hour, again, I have to multiply it with a 60. And in a day, if I want to find how far it can travel in a day, I have to multiply it again with a 24. And if I want to find out how far it can travel in a year, I have to multiply it again with a 365. So if you calculate this number, this product, something like 3 lakh into 60 into 60 into 24 into 365, then you get a number. You can do it later, okay, don't worry. And that much kilometer is called a light year. So that is called, that huge number is called light year. So instead of using that big number, astronomers can easily use that simple number called 1 light year. So easy. So that is why. So here you can see that the nearby stars mean 10 square. 10 square means 1 followed by 2 zeros. So up to 100 light year, you can use parallax method. Now here you can see 10 raised to 5. This is a kind of a notation that is used in not just in astronomy, in science generally. So 10 raised to 5 means 1 followed by 5 zeros. So up to this light year, that means 100,000 light year, you can employ main sequence fitting. And beyond that, up to 10 raised to 7 light years, that is 1, 0, 0, how many zeros? 7 zeros. That is 10 million light year. I can use something called the Cepheid variable method. Okay, then up to 10 raised to 10 light years, okay, that means 1 followed by 10 zeros or 10 billion. Okay, for 10 billion light year, I can use this method called the white dwarf supernovae or Tushy-Fisher rotation method. Okay, just leave those things. Okay, anyway, we will discuss this supernovae method today, don't worry. Then beyond that, we use something called Hubble's law that you will learn it later. Okay, so these are all the different kind of methods astronomers employed for measuring distance, and this arrangement is called the cosmic distance ladder. So here distance ladder means to measure certain distances, we have to use certain methods. Okay, so we cannot use the radar ranging for measuring the distance to nearby galaxy or even to the nearby stars. So if you want to measure the distance to nearby stars, then you have to use parallax. You cannot use the radar ranging method. So the parallax method here won't work to won't be possible or cannot be used to measure the distance to nearby galaxies. For that, you have to use the Cepheid methods. So that arrangement, that or that way of measuring things separately or different distances, we have to employ different methods. These are called cosmic distance ladder. So let's see some of them one by one or in detail. Okay, so you can do this experiment right now. Just hold your thumb like this. Maybe you don't have a car there, but you can do this thing. So I will give you an example. So imagine this is your, okay, this is your, sorry, this is your eye, okay, and this is your face. Assume that this is your face. I'm sorry, this is not your face. Let it be my face. And you can hold your thumb here, okay, just some few centimeter away, or a pen or your thumb like this, and just in front of your nose, okay. Then close your right eye and see where it is, okay. Then see that finger. Then close the left eye and see through the other eye, okay. So close the right eye and see through the left eye, then close the left eye and see through the right eye. Now you can see that finger is actually making a shift, something like this. It will jump from one point to the other, okay. It is something like this. You can see that jump. And after doing this experiment by placing your finger near to your eye, the next step you can do is that you can place your finger a bit farther away, something here, or maybe at an arm length. Then do the same experiment. Close one eye, close another eye, close one eye, close another eye. In both cases, okay, when the thumb is closer to your eye, you can see that shifting, that jumping of finger. And if when it is farther away as well, you can see the what is the jumping, okay. In both cases, you can see those jumping, and when it is farther away, the jumping is small. When it is closer to your eye, the jumping is more. So that means when an object is farther away, okay, like your thumb, when the thumb is farther away, that jumping is small. When the thumb is nearer to your eye, that jumping is more. So in a way that we can say that how much shift your thumb make is depending on how far away your thumb, okay. What are in relation? So the relation is between how far your thumb, okay, is related to, okay, is related to what? Yeah, this is a symbol of related. It is related to how much the shift, the jumping, how much the jump of finger. So the jump and the distance are related, okay. So this is just for the case of your hand. There is no need to measure, no need to use this method or anything to measure the distance to your thumb. But the similar thing can be used to find the distance to a nearby star. I will give you an example, okay. You can see that, okay, here in this case, just leave these equations and all, this will be a bit complicated for you. So take this case. The sun is here, okay, and the earth is here, okay. So just take it one by one. So when the earth is here, we are actually going to measure the distance to this yellow star. You can see this star, okay. We want to measure the distance to this star. And when the earth is here, okay, we use a telescope or something, use a telescope and observe the stars, okay. And this star is actually nearby, and all the other stars that you are seeing in the white, they are actually far away, okay. So we get a picture like this. So that part of the sky will look like this, you see, okay. That means you got a star here, okay. So that is the first picture that is taken in January. Then after 6 months, the earth can travel through its orbit and come to the other side of the sun, okay. Then again we observe the same star and we take another photo. So now you can see that in the first case in January, we observed in this direction, so that the background of the stars are something like this. Background of the yellow star is this, okay. So you can see when you are viewing from this side, the background is something like this, what you are seeing here. But when you come here in July and observe, you can see that the stars are actually, the background has been changed. Or in another way, we feel that the stars, the yellow star is actually made a jump. Okay, compare these two picture and you can see that jump. So it was initially here in January, and in July it jumped to here. So we got that jump. What we did, so the experiment is so simple to say, in a sense, that is, we have to take the picture of the same star, same nearby star, at 2 different months, that is 6 months apart, in January and July. Okay, maybe you can also do that February and August, it is fine. Anyway, we are taking it January and July, and in those pictures, like the finger or the thumb that is jumped, the star will also do the jumping. And due to that jumping, or from those two photos, we can accurately calculate how much it jumped. Okay, from that jump or that shift, how much it is jumped, you can find an angle here. Okay, so we are making a triangle here. So what is the distance of this? This is the distance between Earth and Sun, that is 150 million kilometer. Okay, so we got 150 million kilometer, or which is called a 1 astronomical unit, or 150 million kilometer. So from that 150 million kilometer that we know, but yet we don't know the distance to the star. We know only the distance between Earth and Sun. Now we need to calculate this angle. So this angle can be found out from the jump between the stars. So if you put those two images together, you can see the one star is here and the other star is here. So this is the shift. From that shift, we can calculate this angle. So once you know one angle, if you know this angle and if you know this distance, by using the science of the mathematics of triangles, you can actually figure out this distance. Okay, you can actually figure out this distance. So this is the method called, this method of measuring the distance using the mathematics of triangles is called the parallax method. Okay, this is called the parallax method. But there is a drawback. This is so simple and easy, but the problem is that it is actually not applicable to the entire stars, even in the Milky Way. So it only applies to the nearby stars for Sun. Okay, if the stars are so far away, the parallax or this angle becomes so tiny so that we cannot even measure it. Okay, so that is the problem. So this is the method called the parallax method, using which we can measure. So I will give you another example here. You can see in January the Sun is here. Okay, the Sun, Earth is here, and we are measuring the distance to this star, and the picture of the star is here. Okay, and in July, again, we are observing it from here. So the background changes, the star is shifted to here. And if we combine the two pictures, you can see this is the shift. So from this shift, okay, we can measure this angle, and from this angle and the distance between Earth and Sun, we can calculate this distance. So this is the method that we use, the astronomers use to measure the distance to nearby stars. But the problem is that this is not applicable to all the distances. Like if you want to measure the distance to another galaxy or something like that, we cannot employ this. So there are other methods. So this is a simple problem, leave it, it is not for you. Okay, now let's go and find the second method. Okay, so this parallax method is only applicable to the nearby objects. So now we are going to find out another method. So to learn that method, we need to understand two important terms in astronomy. Okay, so those two terms are luminosity and flux. Okay, the first term is luminosity. So luminosity is the total amount of energy emitted by an astronomical object per second in all directions. So suppose that there is a star like Sun. Okay, a star is there. Okay, so the star is actually emitting, we know that it's emitting energy. Okay, and that energy being emitted continuously. The Sun is still emitting, even though if it is night or day, it is actually emitting light. Okay, that light is a kind of energy. So the total amount of energy that Sun emits or any object emits every second is called the luminosity of that object. So what is that? It is the energy emitted by an astronomical object every second. Okay, in the case of sun, you can see that this much energy is emitted by sun in every second. You can see that is 3.8 into 10 to the power 26 means 1 followed by how many zeros? Yeah, 26 zeros. That much joule of energy is being emitted by sun every second. Okay, so that is called the luminosity. Now we know that even though the sun emits, or any star like that emits this much amount of huge energy, we won't receive it completely. So we cannot even imagine that receiving that entire light, entire energy as such to the earth will evaporate for sure. So since the sun is so far away, we won't get that energy completely here. Okay, so that means we get only a part of that on the earth's atmosphere or earth. Okay, maybe if you are using some kind of a measuring instrument, to that measuring tool or that instrument, we are only receiving a part of, a tiny part of that energy. So that part of energy which is received here is called flux. Okay, so this is the energy really emitted from there, but the part of which we receive here is called flux, or in formal definition, it is the amount of energy from an astronomical object, okay, and that is passing through unit area per second. Okay, it is an apparent, okay, it depends on the distance. Okay, just leave it. Anyway, you can imagine it like the sun emits a certain amount of energy from there, but out of which we get, and that energy emitted by the sun or a star is called a luminosity. But from that heavy or large amount of energy, we receive only a part of that. That part is called flux. Okay, that is a simple definition. So luminosity is the amount of energy emitted by the object, and flux is the part of which we receive here on earth. Now there is an interesting connection between these two quantities. Okay, so just leave it and just imagine that there is a light here. You can see a light bulb is here, and when you are near to this light bulb, okay, you assume that you have a paper or something like that. The paper gets some light. Okay, you know that. Suppose there is simply a paper, and on the surface of that paper you receive some light. Okay, and the actual energy emitted by this light is, imagine that it is 100, but when you are far away from that, you will receive only a part of that, maybe 10. Okay, and if you go even farther, okay, then you will get only, again it will diminish, or you will get only some maybe 2 or 1.5 or something like that. Okay, so as you go farther and farther away from an energy source, you will get only lesser and lesser amount of energy. Okay, that means if you get a certain amount of energy from a certain distance, okay, or the distance or the amount of energy that you get depends on distance. That amount of energy received is called flux. So the flux depends on the distance. Okay, so as you go farther away from an object, you receive only a tiny amount of energy. So the flux is dependent on distance, or in another word, we can say that luminosity and distance are connected. Okay, using this equation. Just leave this equation. It is not for you. It is for higher class students. They can learn. But anyway, I have included, that's all. So the flux and luminosity are connected so that if you know what is the actual light emitted from an object and how much we receive here, from those two quantities, actually we can measure the distance. Okay, so the distance is related through an equation or through luminosity and flux, or we can say in another words, luminosity and flux are connected through distance. So if you know the luminosity and flux, then we can calculate the distance to an object. So once you understand this equation in your higher classes also, then you can easily find out. So this is the connection between F, this is the flux, and L is the luminosity, and R is the distance to object. So if you know some mathematics, you can rearrange this equation and find out what is. Okay, just leave that. This is just, I have just given the equation, that's all. Just leave that, don't worry about these equations or anything, but this is the idea of that. So the flux and luminosity. What is luminosity? Actual energy emitted. What is flux? The energy received here on earth. So the energy received here and the energy actually emitted are connected through an equation, or they are connected through distance. So if you know what is the actual energy emitted from there and what we receive here, using those two things, then we can calculate the distance. Okay, so that is called the uh, one method. But the problem is that we need to know about what is the actual energy emitted by a star. Okay, then only we can calculate. Flux is so easy because flux is the energy that we receive here. We have to put a telescope and then we can measure how much energy we are receiving from a distant star or something. It's so easy, no problem. But you want to know the luminosity. What is the actual energy emitted? We cannot go there to measure how much energy is actually coming out of it, but without going there, we have to find out what is the actual energy emitted. Once you know that, it is so easy to find out the distance, but it is not that easy. That is why the distance measurement is not that easy. So the first that kind of thing which the luminosity is already known is called the Cepheid variable stars. So it is actually initially found out by a famous astronomer, a women astronomer called Henrietta Swan Leavitt, and she actually find out an interesting thing. There are some kind of stars which its brightness will increase and decrease. So it will be brighter at some time and the brightness will decrease. Again, the brightness will increase, then brightness will increase, decrease, increase, decrease. This will happen. Okay, something like this. So for the brightness, so you can find out when the brightness was maximum, again it becomes the minimum, then again it becomes maximum. So we can find out how long it take for two consecutive maximums. So from that we can find the period or the time taken for a nearby peak brightness. Okay, so from that actually we can measure the actual luminosity of that object. So this period, or how long it takes for the pulsation or the brightness change, then from that we can find the energy emitted from that star. So using that we can actually find out what is called the luminosity we got from the pulsation time or the pulsing time. You got that what is the luminosity, and from that you can find out what is the flux. Okay, what is the distance to those objects. So objects that are like this, okay, something like Cepheid variables are called standard candles. Okay, so one method is Cepheid variables. They are variable star. Variable means its brightness is changing. So based on the time it takes for the brightness to change, we can measure the luminosity and we can measure the flux. Using the flux and luminosity, we can actually calculate the what is called the flux luminosity. Yeah, we can calculate the distance. So that is the one method of Cepheid variables. And there is one more thing, you know, that we will learn what is a supernova later. So type 1 supernovas are actually classified into different kind of supernovas. Are actually kind of explosion at the end of a star's life. So there are some kind of supernova called a type 1a supernova. When a white dwarf star, okay, what to say, gets energy or mass from a nearby star, and finally its mass will keep on increasing, and finally the white dwarf will explode like a supernova. And in that case, you can find out the actual luminosity of the supernova again. So from that luminosity, or what is the actual energy emitted from the supernova, we can find out the flux, and from the flux we can find out the distance. So flux we got, luminosity we got. So these are the different methods that we employed to find the distances. Okay, but here I know that many of the things that's like these equations, this period and all these things are actually not that easy to grasp for you, because you are all junior level. So but the idea you have to understand something like, if you know the actual brightness of an object and what is the light we receive here, what is the actual energy coming out and what is the energy we receive here, from it we can connect and find out the distance. Okay, and the objects for the astronomical object for which we know the actual energy emitted, they are called the standard candles. Okay, so one example is the Cepheid variables, another example is the type 1a supernova. Okay, so that's about today, and I will get the questions one by one from the chat, and if you have any more questions you can put it here. And oh, okay. The first one, actually, how can infrared camera detect temperature? So infrared is a kind of, it is also called a heat radiations. So during the corona time or the COVID pandemic time, you know that when you go to some places, your temperature is being monitored, but not just using a thermometer. Usual thermometer cannot be used at that time because it make contact between people. So they use a kind of a gun-like thermometer, and in that thermometer, actually that gun actually receives infrared from your body. So every object, okay, has a certain temperature. So I have a body temperature, you have a body temperature, and the material, your phone has a temperature, or your maybe your table or pen, everything has a temperature. So anything that has a temperature will emit some kind of light, especially our normal day-to-day life things that has a certain temperature will emit infrared. That infrared can be detected, and based on the type of that infrared light, we can measure the temperature. So the best example is that temperature gun that we use. Okay, that thermometer, the gun like thermometer that we used during the pandemic time. So what are neutrinos? So neutrinos are some kind of tiny particles. They are called fundamental particles. So you know that when you divide something, or something like, if you, what you say, fundamental particles means, if you divide something, if you take a pen and divide it into two, it becomes two, no problem. Again, take the other half and again make it smaller and smaller and smaller, chop it again, then you will go to something called an atom. An atom consists of protons, neutrons, and electrons, and that electron is called a fundamental particle, in the sense that you cannot split it again. But proton, you can split it again to get some other things. Similarly, so scientists are actually in search of those kinds of things what are fundamental. So fundamentally, all the objects, what is the world made of? What are the fundamental objects? So from that experiments, they found out another interesting particle called a neutrino. Okay, they are so tiny, and during the nuclear reactions, or the reaction that are happening in the core of sun and all, it is actually emitting a lot of what is called neutrinos, and we can detect it here. Okay, so we will discuss that in the coming session about stars. Okay, so okay, what are gamma rays generally observed in the universe? So I hope you remember when Edumitra introduced to me, you might have been heard a word high energy astrophysics. So, and also gamma ray burst. So when there is highly energetic events like the collapse of two black holes, maybe the collapse of two neutron stars, something like that happens, they are called highly energetic events in astronomy. And during those highly energetic things, this kind of energy or high energy is emitted. So where high energy means, it is not the brightness, it is about the gamma ray. So out of that, I will show you that once again. You can see that, and an interesting thing is that when we start from here, just leave the nm things that I will explain later, don't worry. So from gamma ray to X-ray, when you go like this, the gamma rays has the highest energy. X-rays are lesser in energy, ultraviolet again lesser, and radio waves are so weak. Okay, so gamma rays are the highest energy. So in high energy events in astronomy, there will be gamma rays are coming. So nm means it is called a nanometer. Okay, nanometer means it is another unit of measuring distance. So it is actually, if you take a 1 meter and divide it with a small number 10000 3, 5, 6, 7, 8, 9. That means simply billion. Okay. So if you divide 1 meter with a billion, or that is called a 1 nanometer, or in another word, we can say that it is 1 billionth of a meter. Okay, 1 billionth of a meter is called a nanometer. The triangle method, the methods that is used for finding the distance using triangle is not Pythagoras theorem. It is something like, I will just give you the word, something called sine theta, cos theta, like things. Okay, you will learn it only when you, maybe after 2 or 3 years, you will learn in your school classes. Don't worry about it. Okay. This is called a cosmic distance ladder. Okay. So measuring distances using radar ranging, won't light take different times to reflect back from Venus and leave? No, actually for radar, based on the size of object, the reflecting will change. That's all. Actually, there will be some error will be there. That's for sure. But when you are measuring the distance to a planet, which is actually thousands of kilometers or lakhs of kilometers away or crores of kilometers away, of the order of millions, okay, millions of kilometers away, then small errors like maybe 100 kilometers won't be a problem. Actually, that is a problem. Even for all the methods that I discussed here, the parallax method, the Cepheid variable method, all this has actually a high amount of error is associated with. Will recording will be given? I think it will be given. I don't know. Okay, that I have explained. But won't a light year be affected by the atmosphere of selection? Light year won't be affected by the atmosphere of celestial objects. That is not a problem, because light year is defined in a way that, like, we are assuming that the light year is light is traveling completely through vacuum. But anyway, when you measure the distance to other objects using any of the method, since that light is traveling through the space, even though we say that it is empty, it is not completely empty. Especially in this large distance, it has to encounter different small molecules or atoms like that. So those atmosphere or those kind of things are actually affected. So that it is actually a problem in distance measurement. What does 10 raised about 10 for light year means? Okay, just leave that. You will learn that method of scientific notations later. So that is why I'm not. So can you explain the flux again? Okay, just wait, I will do that. So watt and joule. So joule is actually the unit for measuring energy. So energy per second is called a watt. Okay. So these are two different units. One is to measure the energy. One is to measure the energy per second. How can we measure the luminosity? Yeah, luminosity measurement is a problem in astronomy. That is, we cannot go directly there and measure, but there are objects like the Cepheid variables. If you know the period, then we can know the actual luminosity. And in type 1a supernova, if you know the when is the peak brightness, from that peak brightness time, we can actually infer the what is the luminosity. So these are all some objects for which we already or in using some other methods we can find the luminosity. How does the star jump when it does not go? Here the star is not jumping. Okay, so sorry, don't take it like that. The star is actually not jumping. Star is still stationary. You see this image or this image, you can see that in this image the star is not jumping. The star is here. What is moving actually? We are actually moving. This January and July, we are actually looking it from two different perspectives, like the finger. So when you are placing your thumb in front of your hand and doing this experiment, actually the jumping is happening not because of your hand is moving. The hand is still, or the thumb is still stationary. The only change happening is that you are looking through two different perspectives. That means you are using the right eye and then the left eye, right eye, then left eye. So like that, that is why that change is happening, that shift is happening. Otherwise, there is no shift. So from that shift, we can measure the distance. So the star is not jumping at all. So I will explain the flux actually. So luminosity, again, it is easy, I think, in the sense that that is the energy emitted by an astronomical object. Okay, and you know that the sun is there. Okay, suppose the sun is the astronomical object, so that sun is emitting a huge amount of energy, but all that energy is not received on the Earth's surface. Okay, you get only a part of that. What part of that is received here, or how much we received here, is called the flux. So actual emitted is called the luminosity. What we receive here, it is called the flux. Okay, and they can be connected via distance. And from, if you know the luminosity and flux, then we can measure the distance. So what does black mean in the infrared peak? In the infrared peak, actually it is a kind of, yeah, black means there is no radiation is coming, or it is so cool actually. So its temperature, here you can see that is the, what is the temperature of that. So if it is some 20-degree, okay, you can see that 20, 26, 24, something like that. It is, if it is 18 or below, then it looks like black, that's all. Okay, and if it is some 32 or above degrees Celsius, then you will see it as some pinkish color. Okay, that's it. And red means some 30, 32. You can see that code here, color code is there. Why can't we see anything past visible? Okay, because you can see that that is how evolution works. So apart from the radio waves, you can see here almost all the light that we receive here is invisible, and we want to, as a as we evolved in the Earth's surface, there is no purpose in seeing in gamma ray or ultraviolet or infrared, because we are not receiving it here. And if you have that advantage, it may be an advantage for some other animals. Maybe, I don't remember exactly, some other animals has some power to see some part of the infrared and all, something here, not completely. Something like snakes are able to see in infrared. Okay, so it depends on how we evolved. So for evolutionary, we, most of the light what we receive here is invisible, so we evolved for that, that's all. We are not evolved to become astronomers. Okay, sir, what is the angle called formed in parallax? That certain angle formed itself is called a parallax, okay, or parallactic angle or parallax. So this angle itself is called a parallax. That is why it is written parallax here. Okay, so here in this figure you can see that that angle itself is called parallax. What is atmospheric opacity? So opacity means how much an object allow the passage of light. Okay, so here light means all the types of light. So atmospheric opacity means how much does the atmosphere allow the passage of a certain amount of light. Here you can see in the case of gamma ray, it is complete 100% opacity. That means it is 100% opaque. Okay, here at the same time for radio wave, here that boundary is not here, it comes here. That means it is 0. That means 0% opaque or 100% transparent it is. So opacity means how much does an object blocks light. Atmospheric opacity means how much atmosphere blocks light. Flux, I will once again explain. So flux is actually, it is not FLAX, it is FLUX. I think am I right there? Yeah, FLUX. It is not FLAX. Okay, so that is the energy that we receive here on Earth's surface. Third slide means I don't know. Can you specify what is the content of that third slide? This is the first, second, this is the third one. There is nothing there. This, I don't know. You just message me which one. Okay. Does the sun give? Yeah, the sun also gives infrared radio waves. All the wavelengths are actually emitted by almost every astronomical object. But it depends where it peaks, or what is. Not all the types of lights are emitted equally. Some will be emitted in a high brightness, in some will be minimum. So in the case of sun, actually, it is mostly emitted in visible light. It doesn't mean that it is not emitting in other, it's also emitting, but the brightness is less. Oh, sir, can you explain the first 30 minutes? It's not possible, bro. Sorry. So that parallax angle is actually calculated from that shift. Okay, so you got that two positions. So this is the position 1 and position 2, and you know the background. So based on the background and using some coordinates like right ascension, declination, etc., which I am not going to explain here. So based on this shift, okay, maybe you can use some simple softwares, or you can actually do some not simple softwares, using some analysis called astrometry and all. You can find out how much it shifted in angle. Okay, some angle called right ascension and declination. Then you can, from that you can get the time. So supernova we will discuss later. At that time I will explain what is gamma ray burst. I have already almost, when there are merging of objects that will happen, or yeah, yes, that I will explain when we learn about supernova in the coming sessions. Yeah, radio light can be reflected by anything. That's not a problem. Even the flight can reflect radio light. Clouds can reflect radio light. So the Venus can also reflect radio light. It is so when you think about something reflecting, there is no need of a mirror actually. Even when you shine a torch, okay, on just on a piece of paper or something like that, it is still reflecting, but only a part of it. It is not completely reflecting like a mirror. Okay? Even in the case of a mirror, the mirror is not 100% reflecting. So it depends how much it is reflecting back, but still it's reflecting. So ultraviolet is also another kind of light, okay, which is invisible. That's all. Ultraviolet has some that is also some high it is energetic than the blue light. Cosmic distance ladder, I will explain, don't worry, just a moment, I will do that. That's in are dependent on others. That's a good question. Yes, I will come to that in just a minute. Okay, so the cosmic distance ladder, okay, so the distance ladder means here you can see that maybe for some other things in astronomy, some other measurements, we have only one method which applies to every object. But in the case of distance measurement, we cannot employ a single method for measuring all the distances. Okay, maybe to measure the distance to moon, measure the distance to Alpha Centauri, measure the distance to a farther away star, a near Andromeda galaxy or galaxy clusters. All these things we cannot have a single method. Okay, that is a problem. So every method has its own limitations. So the radar ranging, which applies only to planets inside the solar system, but especially inside inner planets, and that can that has the advantage that it is much more accurate than the parallax or the main sequence method or the Cepheid variables. But the problem is that it can only be used within the solar system. So we have to find out another method which is called the parallax method. So parallax method is good for nearby stars. Okay, and somewhat there is another advantage. It is actually connected. Okay, sometimes there will be overlaps in between. So for some stars we can use the Cepheid method, and at the same time we can use the parallax method. So there some part it is actually connected, or the main sequence fitting can be used for the same star. We can measure even the parallax method as well. Okay, so they are connected in a sense, and the connection is so useful as well to verify whether a new method. So suppose that the initial method was parallax method, and then people found out the Cepheid variable method. So to make sure that the Cepheid variable method is correct, they have to use the parallax method for that. Okay. So that is how it is evolved. So they are actually interlinked or connected, and but for a very far away, we cannot even think about the parallax. Not even think about it. How many types of satellites are there? That depends on how you classify. Okay, satellites are there depending on the use. That means the purpose of the satellite. We can classify it into different kind. Okay, the communication satellite, navigation satellites, maybe astronomical satellites, like that. We can classify them, and based on the orbit, maybe the low Earth orbit, medium Earth orbit, geostationary orbit, some other kind of orbits are there. So it depends on what basis you are classifying. When the light travels in space, what will happen if we get reflected with some other celestial body instead of what we want to get it? Yeah, if you want to observe when the light travels in space, what will happen if it gets reflected from some other celestial body instead of what we want to get it reflected from? So that's the problem actually. So if something like that happens, we get a wrong distance. So for that, astronomers will make sure that what it is. Cepheid variables. Okay, Cepheid variables are, so you know that variable means I don't know whether you know that variable means variation. Simply, variation means change. So something changing is called variable. And here, what is changing for a Cepheid variable is its brightness. If you observe a variable star for a long time, its brightness keep on changing. It will increase, decrease, increase, decrease, increase, decrease. So there are different kind of variable stars are there, and out of which this Cepheid variables, the speciality is that their uh, brightness will vary periodically. That means in a certain time gap it will keep on changing, and based on the time it take to change the brightness, we can actually infer the real light or the what is the total energy emitted from that as well. How will the jumping be happening? Jumping is happening just because of the perspective is changing. So ultraviolet again is a type of light. Okay, you can search and find out what are the application for that. Just a second. Mm, the Hubble's law is the last part of the Hubble's law is the last part of, or the for some distance beyond that, then we need to use the cosmic distance ladder. Lambda means wavelength. Just leave that. Don't worry about those things. Cepheid variables are X-ray. Okay. X-ray is used in hospital. Why is not absorbed by atmosphere around us? Okay, X-ray is used in hospitals. That is, the atmosphere is actually absorbing the X-ray that is coming from the space. Okay, which won't reach here. But we are artificially making X-ray lights. Okay, light in the sense we cannot see directly, but X-ray flashes are there, flashlights are there. They are using for hospitals. Okay. Earth is also giving many kind of rays like Earth, especially infrared, and the light is also the light falling on Earth is being reflected back, and it is reflecting in two different ways. Something direct reflection, and also there will be light is emitting in form of infrared as well. Tree height is not related to parallax, but it related to triangles. Okay. Cepheid variables I already explained. So okay. Minute satellites are there, sir. Types of satellites, it's not that easy. On what basis, that depends. Okay, anyway, it is not part of this syllabus. Are the distance measured by parallax methods accurate? Yeah, accuracy depends on, there are errors actually, but it is the permissible error. Okay. So we cannot say that it is accuracy. That depends on what you need. Okay, or what is the context. So anyway, for every measurement, even if you are using a scale to measure the distance on of a line on your paper, still there is error. Okay. So what letter did written in the Hubble's law formula? Don't worry, Hubble's law formula we will learn in the last session. So don't worry about those things. That is why I haven't explained it in detail. Hubble's law method you will learn in the last session. Sounds and lights are not interconnected. How many types of satellites? Again, I am asking you on what basis? Like James Webb Space Telescopes or Hubble Space Telescope, there are many astronomical telescopes are there. I cannot say that how many types are there. So which variables I have already explained. Then recording of the class, I'm not sure about that. That you can contact with Edumitra. After Hubble's law, there is nothing. That is the final step of the ladder. The Doppler effect is not related to distance ladder. We will learn it later. Okay. But optical telescopes means usually that term optical is used for the telescope that are observing in what is called what to say. Yeah, it is in optical telescope means the telescope that are mostly observing in visible light. Okay, so they are usually called as optical telescope. But many of the professional optical telescopes are also observing some part of the infrared as well, but mostly they are observing in the visible light. That is why they are called the optical telescope. What will or can be done if a distance cannot be measured by the Hubble's law either? So there are no such limitation as of now. Anything beyond can be measured using Hubble's law, because Hubble's law is like that. It related to the size and expansion of the universe itself. So don't worry about that. Anyway, as of now, there is no problem like that. But apart from this, scientists are actually in search of maybe whether to get another kind of what is called standard candle, like the type 1 supernova or type Cepheid variables. If they get better standard candles, it's actually good. What are the telescope used in Hubble Space Telescope? It's a telescope. Basically, Hubble Space Telescope is an optical telescope which is able to see in visible light, some infrared, and some ultraviolet. You can call it as an optical telescope. No problem. So that is for today. Now it is 7. I hope I have answered almost all of them. Something like neutrino, supernova, those things I haven't mentioned because we will learn it in detail later. And the Hubble method of distance calculation, that we will learn it later. So later in the sense, in this week itself. Telescope used in James Webb telescope. So what telescope used in James Webb? That question itself actually wrong. Okay, because James Webb Space Telescope itself a telescope. We can ask what type of telescope it is. Okay, so what telescopes are used is not a right way of asking that question. What type of telescope it is, we can call it as an infrared telescope. So James Webb Space Telescope is an infrared telescope which is able to see infrared. Okay, so that's for today, and see you all tomorrow. And I will explain the remaining methods of measuring some velocity, all those things we will discuss tomorrow. And tomorrow, I think, yeah, we can discuss it directly later. Okay, so that's for today. Thank you.